Okay, let's unpack this. Today we are diving into, well, one of the most fundamental concepts in all of chemistry, really. We're talking about the hidden engine of energy change, exothermic and endothermic processes.
Right, the stuff that makes things feel hot or cold.
Exactly. And for you, the curious learner, just knowing that a reaction feels hot or cold, it's not enough, is it? We need to get beyond that observation
Beyond the temperature change.
and understand the driving force behind it. So our deep dive today is all about giving you that conceptual foundation, the insight, and the exact language you need to really master this topic.
The mission here is to simplify something that can seem quite complex.
Yes, we want to move past just describing the symptoms, like, reading a thermometer, and start explaining the actual cause at the atomic level.
The mechanics of it.
And here's the hook we're going to start with. Every single chemical reaction is a two-step drama. It involves destroying the old and creating the new.
And the energy balance between those two acts, that determines everything.
So where do we start?
Well, what's fascinating here is that the foundational rule is deceptively simple, but it is the key that unlocks the entire subject. When people talk about chemistry and energy, they often jump straight to heat.
Right, so first thing you notice.
But you must start with the bonds. The rule that governs all of this is very precise. Energy is required to break bonds, and energy is released when new bonds are formed.
That's it. That's the core idea.
That is the whole game. And we need to establish this distinction right at the top. You should always visualize a chemical change as like an economic comparison between two steps.
An energy transaction.
Exactly, an energy transaction. So step one is your investment.
Okay, so the cost to get things started.
Yes. You must break the old molecular links in whatever you started with, the reactants. It's a literal pulling apart of atoms that are attracted to each other.
And that takes effort.
It takes energy. You have to put energy in to overcome that attractive force. It's why, bond breaking is always, on a micro level, an endothermic process. It absorbs energy.
You have to pay to play, essentially.
That's the cost. Then step two is the payout.
Okay.
Once the atoms are free, they rearrange into new structures, the products. And when these new stable links are formed, energy is always released.
Why is it released?
It's just a natural release of energy when things move into a more stable, lower energy configuration. So bond forming is always exothermic. It gives energy off.
So the final result, whether the beaker gets warm or cold, is just a net calculation. You're just comparing the energy you had to put in for step one
The destruction,
against the energy you got out during step two.
the creation.
Yeah.
Precisely. And this is the conceptual shift that, it separates the novice from the expert.
How so?
We know from our sources that so many students, even ones who know the definitions, they lose marks because they just describe the temperature change.
The beaker got hot.
Exactly. Instead of explaining the underlying energy changes connected to the bonds, the temperature change is the result. The bond activity is the explanation. You master the bonds, you master the topic.
That makes perfect sense. And once you have those two steps, downbreaking needs energy, forming releases energy, the definitions of exothermic and endothermic just kind of fall into place, don't they?
They do.
So here's where it gets really interesting. How does that balance actually determine the final outcome? Let's start with the first one, exothermic.
The one most people are familiar with.
Yeah, the name itself, exo, it implies something exiting. So in an exothermic reaction, the energy released from forming new bonds, that payout, is greater than the energy it took to break the old bonds.
So you got more back than you put in. Think of it like a business venture where the profit it blows away the startup costs.
I like that analogy.
You invested a little bit to break the old bonds, but the new bonds that formed were incredibly strong, and they released a massive amount of energy.
So there's a surplus. And since the reaction gives out more energy than it took in, that excess energy has to go somewhere.
It's transferred to the surroundings.
Right. And that's what makes the air around it or the beaker itself feel warmer.
Mm-hmm.
We think of things like fire or an explosion, which are just really, really fast exothermic reactions.
But they don't have to be fast.
No, not at all. Think about something much slower, like rusting. When iron rusts, it's actually releasing energy.
Just very, very slowly. You can't feel it.
Right, but it's a classic exothermic process where the energy released from forming those new iron-oxygen bonds is greater than what it took to break the original bonds apart.
And if we contrast that with endothermic, the situation is completely reverse.
The opposite transaction.
Exactly. In this case, the energy you need to break the old bonds, the cost of destruction, is greater than the energy you get back when the new bonds form.
So you're running at an energy deficit.
A huge one. You paid a massive amount of energy to pull the old molecules apart, but the new molecules that formed are, I don't know, maybe they're weaker or less stable, so they only released a small amount of energy.
The reaction is shortchanged then. It spent more energy than it generated.
Right.
So to cover that deficit, it has to get the energy from somewhere else.
It has to draw it in. It takes energy in from its surroundings.
And that's why the surroundings cool down.
Yeah.
It's not creating cold.
No.
It's actively sucking thermal energy out of its environment, out of the water or your hand, and transferring it into the new molecules.
The classic example is the chemical cold pack, right? You snap it,
Yeah.
and the ammonium nitrate dissolves in water.
And it gets cold instantly.
Instantly. Because that dissolving process needs a huge energy input to pull the salt crystals apart, and it just steals that energy from whatever is nearby. Your skin, the water, anything.
And just for a quick memory aid, because prefixes always help, it's about the direction of energy flow, isn't it?
It is.
Exo means energy exits the reaction. Endo means energy goes into the reaction.
Yeah.
If you just remember that entry-exit dynamic, you can figure out any question on this.
And if we want to, connect this to the bigger picture, this whole two-step process can be visualized perfectly with something called energy profile diagrams.
Ah, the diagrams.
They're not just some academic exercise. They are the visual map of that energy transaction we've been talking about. They show the whole journey.
Now, in an audio format, diagrams can be a bit tricky, so let's try an analogy. Let's imagine the reaction is like a roller coaster track.
Okay, I like that.
The y-axis going up and down, that's the energy level. And the x-axis going from left to right is just the progress of the reaction.
Perfect analogy. And on this roller coaster track, before we even look at the final drop or climb, we have to talk about the first hill, that initial mandatory incline.
The big climb at the start.
That is what we call activation energy.
Right.
Activation energy is the minimum energy you need to start any reaction. It doesn't matter if it's exothermic or endothermic. It's the energy cost to get that initial bond-breaking process going.
Every roller coaster needs that first clack, clack, clack up the hill.
It needs a kick to get over that first hill. So the height of that hill on the diagram, that represents the energy you have to put in just to start pulling those initial bonds apart.
Okay, so that's the activation energy. Now let's see where the roller coaster finishes.
Yeah.
For an exothermic reaction, where does the track end?
The products, where the track ends, they are at a significantly lower energy level than where you started.
So the ride finishes closer to the ground than it started. Why?
Because the reaction released more energy than it took in. So the product molecules themselves, they actually contain less stored chemical energy than the reactants did.
And that extra energy.
Had nowhere to go but out into the surroundings, making them warm. The diagram shows that net drop in stored energy within the molecules.
Okay, so exothermic, start high, climb the activation hill, end low.
Precisely. Now, contrast that with the endothermic diagram. Since that reaction had to pull energy in from the surroundings,
Right.
the products end up at a higher energy level than the reactants.
Wait, hang on. So the final molecules have more stored energy than what we started with.
They absolutely do. The new chemical bonds in those product molecules have absorbed and stored the energy that was pulled from the surroundings.
That's why it felt cold.
That's exactly why. The reaction stole the energy from its environment and locked it away as chemical potential energy in the products. That's what the diagram shows.
That roller coaster analogy really helps ground it. It's not just numbers on a page anymore. It's a journey.
It's a journey with a hill and a destination.
So now we have the mechanics with the bonds and we have the visualization with the diagrams. The final piece for real mastery here is communication.
Using the right word.
Yes, our sources really stress this. Using precise, correct language is the critical difference maker. It's not about being fussy. It's about proving you understand the mechanism, not just a result.
Absolutely. If you're asked to explain why a reaction is, say, exothermic, you have to detail the mechanism. You can't just state the conclusion. It needs a structure.
And our sources give us that structure, a three-step process that an expert or an examiner is looking for. First, you state that energy is always needed to break bonds. Second, that energy is always released when new bonds form. Those are the two universal truths.
And the third step, the linchpin, is the comparison. You have to explicitly compare the energy for breaking versus the energy from forming.
So for exothermic, you'd say the energy released is greater.
And for endothermic, you just flip it. The energy required was greater. That comparison is the core of the explanation.
And to really nail that explanation, you need the right vocabulary, the terms that, elevate the conversation.
Right.
You have to use exothermic and endothermic, and you have
Uh-huh.
to replace gets hot with the much more precise energy transferred to the surroundings.
And of course, bond breaking, bond forming, and activation energy, those are non-negotiables.
And just as important as what to avoid, right?
Oh, absolutely. You should never say that heat is created or energy is lost. Energy is conserved, it's transferred, it moves from the system to the surroundings or the other way around.
And the biggest pitfall, which we mentioned at the start, is describing only the temperature change without ever mentioning the bonds.
That's the key mistake. The temperature change is your first clue, but the bonds, that process of destruction and creation, that's the real explanation.
So what does this all mean then? I think the core takeaway is that you now control the fundamental thought process for this.
Hmm.
It's a three-part mental routine: break, form, and compare.
Yes.
If you approach every chemical reaction through that lens of bond energy, the temperature change just naturally follows. It's a necessary consequence of that imbalance, and that is real fluency on this topic.
And thinking about that imbalance leads us back to a really crucial question about control. We said exothermic reactions release energy,
Right, they give it out.
but we also said that every reaction, even the ones that give off a ton of energy, needs that initial input, that activation energy, the
Right.
first hill on the roller coaster. So this raises an important question for you to think about. If a reaction is energetically favorable, if it's going to release energy, maybe even cause a fire, why does it always need that little kick or spark to begin? If it's going to release energy, why doesn't it just happen spontaneously?
That is a phenomenal point. Why isn't every exothermic reaction already running? Why isn't all the fuel in the world on fire right now?
That required activation energy, it acts as a temporary invisible energy barrier. That barrier is the only reason that fuel doesn't spontaneously combust everywhere, all the time.
It's the universe's built-in safety mechanism.
It is. If the activation energy were zero, the world would be a very, very different place, constantly on fire.
So that initial barrier is what gives us control.
Precisely. It's the gatekeeper that prevents uncontrolled, spontaneous reactions. It gives us the chance to initiate them only when and where we want to, whether that's lighting a match or starting an engine. The ability to control that initial energy barrier is the practical power of activation energy. It's what separates a combustible mixture from a controlled source of energy. Just think about how much that invisible barrier protects the stability of the world around you every single day.